Good morning, everyone. My name is Deepika Kancharla, and today I will present my research in evaluating the long-term impact of COVID-19 booster vaccination uptake. This work focuses on using machine learning models to forecast booster uptake at a national level and understand its relationship with hospital and ICU load. COVID-19 continued to evolve, and although primary vaccination campaigns were successfully initially, immunity from these earlier doses declined significantly over time. This makes booster vaccination essential, especially with the emergence of new variants that increase transmittability and breakthrough infections. Globally, we see highly uneven booster uptake. Some countries have achieved stronger booster coverage, while others still struggle due to supply limitations, vaccine hesitancy, and unequal health infrastructure. These disparities leave major gaps in global protection and increase the risk of renewed hospital strain. However, most countries currently lack reliable tools for data driven forecasting. Public health decisions are often reactive, non predictive. My research addresses this challenge by developing machine learning models that can forecast national booster uptake and help link these predictions to real world healthcare pressure. Background of this research, booster vaccination is proven to reduce hospitalization and mortality, yet global inequalities persist. Policymakers currently lack transparent data-driven tools to predict future booster uptake. This is important because vaccination behavior is not linear. It reflects demographic, policy behavior, and behavioral responses. Machine learning enables us to model these non-linear vaccination patterns effectively. The My motivation for this research comes from three realities. Booster uptake is showing despite continued COVID-19 risk, countries face unequal access and unequal protection. Health system require early warning signals to prepare for potential surge. By relying on open global datasets, my research aims to provide evidence-based insights to support public health decision making. Research and aim and objectives. The aim of this research is to forecast national COVID-19 booster uptake and examine how these predictions relate to hospital and ICU load. My key objectives were to develop predictive models of booster uptake to compare linear regression and random forest, to analyze how booster uptake correlates with the hospital and ICU outcomes, and finally to generate policy relevant recommendations. This project integrates three major open data sets: Our World in Data, which provides vaccinations and hospitalization data sets; Our World Organization offering global daily COVID statistics; Kaggle vaccination coverage data sets, which provide country level vaccination indicators. Together, these form a multinational time series data set that includes vaccination, case counts, hospitals, and ICU indicators. The methodology consists of several stages. First was the data pre-processing. I cleaned the data because there was a lot of missing values and random values with null values, and merging all the data sets and scaling numerical features. A second one is a feature engineering, which include lagged vaccination indicators and hospitalization trends to capture time-dependent behavior. Third one is model development. Linear regression served as the baseline, helping interpret linear relationships. Random forest regression allowed us to capture nonlinear interaction based patterns. Finally, model evaluation used R square, MAE, and RMSE to quantify predictive performances. And the research gap, there are four major research gaps existing in literature. Very few studies use multi-country open data sets like WHO or OWID. Many predictive studies have lack of reproducibility. Most overlook behavioral, policy, and socio-demographic factors were not included. Almost none connect booster forecast to hospital or ICU outcome. My study addresses these gaps with transparent, interpretable machine learning methods. Now, The linear regression achieved a strong R-square value of 0.98, but its MAE and RMSE were high, showing that it is struggled to capture real-world booster dynamics. Random Forest performed significantly better. It achieved an R-square of 0.99 and produced much lower prediction error. This result demonstrates that booster uptake is nonlinear and time dependent, and random forest is far better suited for this prediction task. Now, the machine learning models which we use now. Linear regression served as a transparent baseline model, allowing us to see basic linear relationships. However, booster uptake is affected by complex interaction between past vaccination behavior, and the cases were increased rapidly, and sometimes they are decreased as well, and policy responses. Random forest captured these interactions and provides highly accurate prediction with R square, that is 0.996. Here we can see a hospital and ICU impact analysis. When we linked predicted booster uptake to hospital and ICU outcomes, we found a strong and negative correlation. Countries with low booster coverage consistently showed higher hospitality and bed occupancy, higher ICU admissions, and we can see them in this both the graph. This means that as booster uptake increases, the strain on hospitals and ICU decreases significantly, and these results reinforce the vital role of boosters in reducing severe diseases and outcomes. And the visual patterns I showed is clearly show that high hospitals and ICU occupants differences between them. And now the policy implications and recommendations for a better thing to be done. And these findings carry several important policy implications. Early warning systems, machine learning forecasts can alert hospitals to prepare capacity in advance. A targeted communication messaging should focus on communicate with booster hesitancy and equity focused deployment. Prioritizing high risk or underserved population can reduce several outcomes, and operational use. These predictive models can be embedded into real-time public health dashboards. And here we can see the two graphs which shows the results of the random forest achieved the best performance and compared to linear regression, which is lower. And conclusion and the future work, the my study shows that random forest provides a highly accurate and interpretable way to forecast booster uptake. We also established a clear relationship between booster levels and a reduced hospital and ICU burden. This demonstrates how explanation, all paired with open data, I can support large scale health surveillance. And my future work, I plan to explore subnational modeling, integration of a social media sentiment, and automated real time of models. Thank you for your patience. I will explain my code, and I already explained my presentation. Now I'll walk you through this code. Here, first I imported all the library Python libraries which we use in this because we are calculating the statistics of death cases and the hospital statistics. So we are using Pandas, NumPy, and Matplotlib and Seaborn because they are good for mathematics and statistics. And here we are using as sklearn model selection and linear model as well. And here sklearn used for encoding train test split ML models and evolution. Here I fetch the data for four data sets. We are all loaded here, which are the cumulative COVID vaccine booster doses, COVID hospitalization, country vaccinations, and WHO COVID-19 global daily data. In here, we started cleaning all the data because it's a huge data set we are using. So that's why I all ran the code in the Google Colab so that it can run fast. That's what I thought of doing in Google Colab. And here, when we comes to here, we are cleaning all the data in hospital data set. removes missing value, show how many types of indicators exists in the file. And now here a pivot table is converts rows columns for different indicators, such as example entity ISO code date in the format, and the unnecessary columns were removed. So now we can see all the changes here, what we did in the pivot tables code line, and renaming all the columns for ununiformity, because all the files have like a same kind of information of code data date, and we are using all these things to get all the data in good format, and makes merging possible. And now I am merging all the data sets into data time format to get all the dates at one place. It's necessary for time series processing and prevents errors in merging. Now here, preparing WHO dataset to merge all datasets together. Here, merge one is for booster datasets with the country vaccinations, and merge two is the hospitalizations dataset. And you can see the file here. And the final merge is in the final merge we added World Health Organization cases and deaths. And so now we have a one big data set containing boosters, hospital data, vaccination data, WHO cases and deaths all together at one file. And now here all the visualizations will happen here. Global booster trend is the first one I just want to explain here. A line chart showing the booster uptake increased globally. Here the figure size in the 12.12,5, and here booster doses cumulative statistics data set were used, and the title has average global booster uptake over time. In the figure we can see the x-axis we has date, like month and date. In the y-axis we have average total boosters, and we can see as the booster intake increases, here the graph rapidly increases in the in the year of Jan 2022, where different kind of variations was happen. And this one is the graph too for booster uptake distribution across countries among the world. And here x-axis, y-axis are like in the x-axis we placed all different countries like Australia, Canada, Finland, France, Ireland, Israel, everything. And in the y-axis we have booster doses, like how many doses they started giving to the people. And here we have a scatter plot of the figure size 10,6. In the x-axis, we have people fully vaccinated per 100. In the y-axis, we have booster doses cumulative. And here it's a booster versus finally fully vaccinated people percentage. So here we can see in there like 80% of people got vaccinated in the booster doses. The SNS, sorry, in the SNS pair plot, it shows relationship between four vaccine correlated columns. Before this, we saw like different kind of data set files, like hospitalizations and fully vaccinated people and like among the countries. And here in SNS pair plot, we'll see all together like booster doses cumulative, people vaccinated per 100, and people fully vaccinated per 100, and total vaccinations. Here you can see all the graphs in different stages all together. So it's I was showing this visualization because we can see all the changes at a time. Like in the initial stages, they are not really the graph was grown like the dosage was. Like the people get vaccinated more, and later the graph grown frequently. So that I just want to show all the difference together. And here the booster countries trend, it's a booster country trend. top 10 countries with the highest average number of cumulative booster doses, and then visualization how booster uptake trends over time for those countries. It began by grouping the dataset by country and calculating the mean cumulative booster doses for each time. From these averages, it select the 10 highest ranking countries and extract their names. I can show you among here. And the code then filters the original data frame so that each country line is drawn in chronological order using Seaborn's line plot. And the plot data on the horizontal axis and cumulative booster doses on the vertical axis. Here I did few feature engineering because I just want to show difference between the booster uptakes and the hospital occupancy and the hospitalizations, and how like the ICU beddings were having trouble with them, like space for the patients when they need for most. And here uh, the converts data into separate year, month, day when the people are attending, and unnecessary columns were removed. In the x-axis you can see the booster doses, and the y-axis you can see like daily hospital occupancy, and the title was for booster uptake versus daily hospital occupancy. And here it's sort of year, month, day, as I told before. And here we are using encoders. Encoder convert categorical strings into numbers. This code uses label encoder from Skitlearn to convert categorical text data into numerical value, because machine learning models work with numbers rather than strings. First, a label encoder object is created, then fit the transform for transform final country encoded is applied. The encoders scan all unique country names. For example, Australia 0, Brazil 2, India 1. It gives a code. And now I'll walk you through correlation heat map. And this code is used to compute and visualization the correlation matrix of a numeric dataset using a heat map. Calculate the correlation matrix, all columns in numeric. A correlation matrix show how strongly each pair of positive relationship closest to -1 indicates to +1. And the code generates heat map using Seaborn, and the figure size is like 14 comma 10. And here the daily hospital and ICU occupancy variables also show moderate to strong correlation because they measure related aspects of healthcare time-based features such as year, month, day, and how weak correlation with most variables has been showed. In the y-axis, we can see total vaccination, people got vaccinated, and daily vaccination per million for it's for among the world, and daily ICU occupancy. And in the x-axis, as we can see, like daily vaccinations per million and daily ICU occupancy. Overall, the heat map helps identify redundant features, understand scalable grouping, and highlight which relationship may influence and predictive modeling. And here, machine learning models are trained, and the target variables like booster doses, cumulative country, date, and vaccines. And here, data is split into trained data and test data. Uh, the targeted variable y into two parts, one for training model and the one for is testing how well it performed the unseen data. In this case, a test size is 0.25, and we can see here, and the random state is 42. Here we are training like in the scalar standard scalar. Here I implemented a standardization scalar object is created which transform date by subtracting the mean and divided by the standard deviation for each feature. When the scalar is applied, the scalar calculate the mean and the standard deviation. And the same mean and the standard deviation learned from the training set to scale the improve model performances. And here I'm training a linear regression model, and it's predict booster using linear regression and for use for interpretability coefficients. And here in this cell, the I already told in the presentation, I'm using random forest regressor. It ensembles a tree-based model. It shows better accuracy as compared to a linear regression. Handles non-linear relationships as well. And here model evaluation function performances calculate prediction performance R square, it's Q like 0.99, and RMSE value as well. Here you can see the results of logistic regression and the random forest regression, and then applies in the both the logistic regression and the random forest prediction. The function performs, takes a true value and the model predicted, and returns a dictionary containing three evaluation metrics: R square, RMSE, and MAE. Here we can see in this graph the coefficients and the features in the y-axis. And for linear regression, it shows which feature have positive and negative impact. In the random forest regressor, it shows top important features of 15 features. And now it shows the predictor booster versus hospital beds. Yeah, here we go. And another one is predictor booster versus ICU usage. Here in the scatter plot, we have in the x-axis and y-axis daily hospital occupancy and the predicted booster uptake. This code visualizes how predictor booster doses compare to hostel occupancy over time, but it first checks whether the data set contains the data column, and if the data in the column condition ensure the plot is only created if the data information is available. If it exists, the corresponding dates for the test set are added to X test copy by matching the indicates. And here we can see the predictor boosters on the x-axis and in the y-axis hospital accuracy. At the beginning, there is no much booster uptakes were there, and randomly it start decreasing because of taking boosters at right time, so that people won't get affected as easily like before. And here, the two the predicted booster uptake versus ICU occupancy as well. Like before, I showed hospital occupancy, and it decreased gradually. And I will show the final model comparison plots. And this is the predicted uptake versus hospital occupancy over time. And now the two graph prediction versus actual logistic regression and prediction versus actual random forest regression. In this comparison, this code actually generates a scatter plot to visually evaluate how well logistic regression models prediction match the actual booster uptake values. It begins by creating a subplot layout with one row and the two columns, and this plot occupies the position of actual values of y-test and y-axis represents. And here the random forest predictions are more than the linear regression. The title and axis are described here, and you can see the changes between the linear regression and the random forest regression. And my code was up to here, like where I just wanna show difference between hospital and the ICU and the booster uptakes. And I always compared the situation between situation in the hospitals using linear regression and random forest regression. Thank you.